AP Exam Review Lesson 9. In this lesson we'll take a look at equilibrium as applied to acids and bases, a very important class of compounds. So let's do a few multiple choice questions to begin with. This is more of a definition of an acid and a base, and this little mark right here should be a double arrow. So think of that as a double arrow. So the Bronsted-Lowry bases in the reaction represented above. Now this definition of an acid and a base, recall that an acid is what we call a proton donor. And a proton, again, is simply a hydrogen ion, because when a hydrogen loses an electron, all that's left is a proton. A base is a proton acceptor. So these are essentially the definitions. So what we're asking for is the two bases in this equilibrium. Now, if you take a look at NH3, NH3 is actually going from the left to the right. Looks like it is accepting a proton. In fact, taking a look at NH3 on the left here, it becomes NH4+. So it must have accepted an H+, and it accepted that H+ from HCl. So HCl is the acid, and then NH3 would be the base. And famously, ammonia, NH3, is a very famous base. So we definitely know that NH3 is going to be a base. Now looking at the other side, on the right side, recall that we can think of the equilibrium now as going back over to the left side. So let's see which one is acting as a base going back toward the reactant side. And that would be Cl-, because Cl- looks like is accepting an H+ as it goes back toward the left. So we should say both NH3 and Cl- are actually acting as bases. How about this question? A 0.10 molar solution of which of the following salts is most basic? Now, what we talked about is anytime you have an acid, its conjugate base, or its conjugate becomes a base. So, for example, if you have HF as an acid, we can represent this as HF donating a proton. It may be easier to actually react HF with water, because an acid always has to get reacted with a base. So why don't we show it this way? So HF then giving up the H+ becomes F-, and then whatever is left over, in this case H3O+. So this guy would be a base. Again, a base, if we think about it, going back toward the left. But what we said is that the stronger the acid, the weaker the base. And the weaker the acid, the stronger the base. Think of it this way. And in order to have a formidable base, in other words, in order to have an anion that will be basic, you have to begin with a weak acid. And the weaker the acid, the stronger your base is. So if we think about lithium nitrate, nitrate would be your anion that could be basic, but nitrate came from nitric acid. And recall that nitric acid is strong, which means its conjugate on the right side, nitrate, won't be basic, will be so weak as a base that we can consider it as not being a base. So this one's out. Same thing with, you can say, sulfate. Sulfate came from sulfuric acid, which was also a strong acid. And it's a good idea to remember your 7 strong acids. Nitric, sulfuric, we had hydrochloric, hydrobromic, hydroiodic. You also had chloric, HClO4, and perchloric. Actually, this is perchloric and HClO3 chloric. So these 7 acids are considered to be strong acids. And so we can see Cl came from hydrochloric, which is a strong acid, which means Cl- won't be basic. Again, we have nitrate here. So this is the only one that would match. In fact, carbonic acid, H2CO3, is a weak acid, which means its conjugate will be basic. And that's how you would figure this out. So E is actually the right answer. How about a question like this? A 0.10 molar solution of a weak monoprotic acid has a pH equal to 4. the ionization constant Ka of the acid is. So this comes into the idea of, since we're treating now acid-base reactions as equilibrium systems, we can show an acid, monoprotic acid, we'll just call it HA, and as the acid reacts with water, it donates the proton, we end up with A- and H3O+. And the idea is we can now talk about the equilibrium constant, the Ka. And remember, this is measuring how weak our acid is. The lower the Ka, the weaker the acid, because remember, K is products over reactants. So if your K is a low number, that means you have a lot of reactants and not many products, which means the reaction is on the left. So in this case, what we have to do is essentially set up the icebox. And what we're asking for is the Ka. Now, just setting up Ka for this system, Ka is products over reactants. Remember that water is a liquid, so water will not go into the equilibrium expression, but A-, the conjugate base, will, and so will H3O+, and so will HA. So this is our Ka setup. So the beginning concentration is 0.10 molar. We don't care about the water because water is not going to go into the equilibrium expression. A- and H3O+ are zeros. This is always how we treated the icebox. Then we have some sort of change, and we have to lose on the reactant side and gain on the product side, plus X and plus X. Now here we're actually given H3O+. We're actually given this value. So we don't even have to use X's. We actually know what X is. Because we know what X is, why don't we just go from there? So we're actually going to find out what X is. Remember, pH gives you H3O+ concentration. In fact, pH is the negative log of H3O+. Which means if we know pH, we can find H3O+. And if you undo this equation, 10 to the negative pH will give you H3O+. This is simply this equation rearranged. So if we do 10 to the negative 4.0, we actually get 10 to the negative 4.0, 1.0 times 10 to the negative 4. We can write it in like this, or this is actually 0.0001. So, and actually this is a multiple choice question, so that's why you'll be able to solve this without a calculator. You can kind of pull out, remember the negative log pulls out the power, so we have the power here, and it equals this number. So our H3O+ must be 0.0001, which means we must have gained 0.0001 as we went toward the products, and because A- is a 1-to-1 relationship to H3O+, we must have gained 0.0001 here. So this guy is 0.0001. We must have lost this much, 0.0001. And you can do this calculation, and we should end up with make sure I get the right number for the so we get 0.999, which will round essentially to the same as HA, this guy here. And now we can plug this into our K, and remember we want to plug in the equilibrium concentrations because K is the equilibrium constant. So we have 0.0001 squared over, essentially you can say 0.10. And because we don't have a calculator to do this, let's go ahead and think about this. So we have this number here is actually 10 to the negative 4th. So squared, anytime you square that, you will actually end up with 10. Anytime you square, you multiply your powers. So you get 10, essentially you get 10 to the negative 8th divided by 0.10. 0.10 is a tenth, which means we multiply by 10, which means our number is 10 to the negative 7. And this is your answer, 1.0 times 10 to the negative 7. So This question is a good one. It covers how we view weak acids in terms of equilibrium. So think about this one and be able to solve a problem like this. Okay, we'll do a few questions that relate to some experimental based maybe conditions. So this one, actually, this graph we'll use for the next 5 questions, so we'll keep referring back to it. Here it says the pH of 4 acids prepared at various concentrations were measured and recorded in the table below. So notice that all the acid concentrations are listed here, and we can see the pHs. And this down here will essentially be one of the most important pieces for us to look at. Here it says that the 4 acids are in no particular order: chlorous, hydrochloric, galactic, and propanoic. Now all of these except hydrochloric are weak, so HCl is the only strong acid. The rest are weak. So what we are thinking about is one of these pHs is strong. And can you guess which one it is? It's got to be this guy. Here we have the lowest pH will be due to the strong acid. Now this makes sense because pH, remember, is the negative log of H plus concentration. If you have a strong acid like HCl, all of it, by definition, dissociates into H plus and Cl minus. So whatever your concentration of HCl, that's your concentration of H plus. So you can simply negative log that to get the pH, and negative log of 1.0, because that's the concentration, is 0. So we know that this guy right here, acid 2, is good old HCl. And the rest of the acids we don't really know about. So let's take a look at some of the questions and see what they want from us. So 4 says, for which acid is the value of the dissociation constant Ka the smallest? In effect, what we're asking is which acid is the weakest. Because if the Ka is a tiny number, if you have, 1.5 times 10 to the negative 8 or something, this means the acid is very, very weak. And a very weak acid will have a high pH. The higher the pH, the less of the acid dissociates. So really, this is a question about which has the highest pH. Looking back over here, the highest pH is acid 1, because notice 2.44 when we dissolve a mole of it in a liter. So that would be acid 1 for this one. Question 5 says, which of the 4 acids listed in the table is hydrochloric? Well, we just determined that. It's the one that has a pH of 0. All of it dissociates. That would be acid 2. Okay, let's see what else we got. Of the following species, which has the greatest concentration in a 1.0 molar solution of acid 1 at equilibrium? Now, we said that our acid 1 is our very, very weak acid. Very, very weak acid. If you have a very weak acid, by definition, that acid, as it reacts with water and dissociates, remember acids produce H3O+, by definition, if it's weak, then most of it ends up on the left side, which means we have a lot on the reactant and very little on the product side, which means we don't have much of H3O+. That's out. The conjugate of base 1, this guy's our conjugate, or conjugate base of acid 1. We don't have much of it, so that's out. And then the OH minus concentration really isn't here. Now, it is in solution. Anytime you have water, you actually have, remember, this is the auto-ionization of water. You do have an equilibrium setup where you have OH minus and H3O+. But the amount of OH minus will be tiny compared actually to HA. So HA is the one that wins. Acid 1 you have the most of, because just of the nature of the weakness of the acid. See what else we got. If equal volumes of the 4 acids at a concentration of 0.50 molar are each titrated with a strong base, which will require the greatest volume of base to reach the equivalence point? So here we're doing a titration, and we've done a number of titrations. What we call a titration would be you would have an acid here, and then you would add a base from a burette into the into the acid. Now it turns out that it doesn't matter what type of acid it is, whether it's weak or strong. As long as you have the same concentration, you'll need the same amount of base, because even if it's weak, when you neutralize a weak acid, essentially you get rid of a weak acid dissociates, remember again. So when you neutralize, when you put OH into here, essentially the OH neutralizes the H plus and more of the acid dissolves until all of it is titrated. So actually the answer is it does not matter. All the acids will require the same volume of base to reach the equivalence point. And this again is why you can neutralize a strong acid by a weak base, or a weak a strong base by a weak acid. When I say neutralize, like acid spills or base spills in the laboratory, the way to contain them is you pour the opposite weak, because it doesn't matter whether it's weak or strong, it'll completely neutralize it. I think this is the last question referring to that table. A 25 milliliter sample of a 1.0 molar solution of acid 1 is mixed with 25 milliliters of 0.50 molar NaOH. Which of the following best explains what happens to the pH of the mixture when a few drops of 1 molar nitric are added? So what we've got, acid 1, remember, is our weak acid, and this could be the dissociation for it, A minus and H3O plus. So what we're doing is we're adding some base. Now notice we're adding half a molar of the same amount. We have 25 mils, 1 molar and half molar. In effect, what we're doing is we're trying to cut the amount of this in half. Remember, we begin with a little bit of products and a lot of reactants because it's a weak acid. Ka is really small. So what we're doing is we're trying to neutralize. And in fact, as we neutralize this amount, it goes toward the product side. So what we get is we get a good amount of conjugate base. And in fact, if you recall, this means we have a buffer. There's a way to form two ways to form a buffer. You can add the weak and the conjugate indirectly, or you can begin with the weak and then add a base to neutralize it to become the conjugate. Since we have half and half of acid and conjugate base, we have ourselves a buffer. Now a buffer can handle both a strong acid and a strong base, and here we are adding the strong acid. So what will happen is the basic portion of this buffer will neutralize that strong acid. This is the conjugate base, which can actually take in and neutralize this strong acid. So the pH of the mixture stays about the same because the conjugate base will react with it. So this is the best answer. Again, we're dealing with a buffer. And be on guard so you can see and find them proposing a buffer to you. You can see when the buffer is made. One more question and we will wrap this lesson up. The graph below shows the titration curve that resulted when a sample of 0.1 molar monoprotic acid was titrated with a solution of sodium hydroxide. Based on the graph, the pKa of the acid is closest to. Now this is a totally different question, and we actually did a lab like this, except we didn't talk about pKa. So let me show you. The answer is actually quite simple, and then I'll show you the theoretical background behind it. Remember, this point on the titration curve is the equivalence point, the point at which all the acid has been neutralized by all the base. This is the S curve. And what we did is we took a volume that's halfway to the equivalence point. Since the equivalence point is roughly 50, halfway would be roughly 25. And then essentially we took a look at that pH, which gave us roughly 4. The answer is actually 4. The answer is B. Now the reason this works is because at the equivalence point, what we've got, essentially, we've got an acid again, HA, being titrated. So, whoops, it should be H2O. And we got A minus and H3O plus. In effect, we have, at the equivalence point, we have no more HA. All the beginning we have this. This is the picture at the beginning, but at the end, all of this is actually gone, and we just have A minus left. So what we're trying to do is halfway to the equivalence point. These again are half and half. Now, half and half means if you set up the Ka, remember, is products over reactants. In this case, again, A minus times H3O plus over HA. Now, at halfway to the equivalence point, which is this point right here, your A minus concentration, and your HA concentration are the same. So effectively, they actually cross out of the equation, and you end up with Ka equals H3O plus. Now, if you negative log H3O plus, you'll get pH. That's by definition what negative log means. So if you do negative log of H3O plus on the right side, you also do negative log of Ka, and negative log, this negative log operator is actually the P. This is what we mean by the P. So effectively, let's put this equation here, you get pKa equals pH. And so that's why they're asking for the pKa, and you're really just taking a look at the pH halfway to the equivalence point. pKa's are a quick way of checking the weakness or the strength of an acid. And the higher the pKa, the weaker the acid is. And that's essentially the idea. Okay, so this will conclude for us lesson 9 of this review.